Hey, how's it going everyone? Welcome to this video. In the last chapter we've had a look at differentiation, talking about rates of change and gradients of curves. So this is part of calculus, the overall arching principle, and so we're going to have a look at now another strand of calculus, talking about integral, also known as antiderivatives and integration. Essentially what we're doing is we're finding the area between two curves. There's a few steps before we can get there though, but that's what we're going to be looking at in this chapter. So to start off with, the last chapter we had a look at differentiating. So starting with x squared, to differentiate we took the power down and multiplied it, and then we take 1 from the power to get 2x. So x squared, differentiating it, gave us 2x. Now we're looking at going backwards. So if we were starting at 2x, we now want to do what's called anti-differentiate. So it's doing the opposite of it. So going from 2x, we're going to get x squared eventually. But how do we get there? There's a few steps, just like differentiating. It's almost the opposite, the exact opposite of doing it. So to start off with, to be able to find an antiderivative, AD, basically you'd add 1 to the power. So when we differentiated it, we took away 1. Now we're going to add 1 because it's the opposite. So the first step is to add 1 to the power. After that, we divide the function or the equation by the new power. Okay, 2 steps. So add 1 to the power, divide by the new power. So before we had 2x. My first step is to add 1 to the power. So at the moment it's 1. We generally don't write powers of 1, but I'm going to add 1 to it. If I do that, I'll get 2. So that's my first step. My second step is to divide by the new power. So I'm going to divide this all by 2 because that's my new power. And as you can see, the 2's are going to cancel, and that's going to give me x squared. Alternatively, sometimes it gets confusing by dividing. You can also think about it as multiplying by the reciprocal. So instead of dividing by 2, I had 2x, add 1 to the power, that doesn't change. But instead of dividing by 2, I might just multiply it by a half. It does the same thing. Sometimes it's easier to do that, gets the same answer. So two different ways, up to you what you think works best. So that's essentially all we have to do. So add 1 to the power, divide by the new power. Let's have a look at another quick example. So if we have 4x cubed, all right, finding the antiderivative of it, we add 1 to the power. So instead of 3, it's now a 4. The 4 doesn't change, but now I'm going to divide it all by 4 because that's my new power. They cancel and I get x to the 4. And one last one, if we have 3x to the 5, okay, I'm going to add 1 to the power and now divide it by the new power. As you can see, we have a common factor, so it's 1/2 x6. So that's essentially the steps to finding antiderivatives. Now, before I go on, let's go back a step. So before, we know the derivative of x squared is 2x. It's also true that the derivative of x squared plus 1 is also 2x. And we can also say the derivative of x squared plus 1000 is also 2x. So when we go backwards, we get these constants as a possibility. So when we find an antiderivative, we're finding a possible antiderivative. So 2x gave us x squared going backwards, but I could also say another antiderivative is actually x squared plus 1, because that's also true, and also x squared plus 100. So what we need to do is account for this constant possibility. So if we find the derivative, uh, our original function, when we antiderivative, is going to be just y. So if the derivative of 5, the derivative of the equation is 5, well, the original equation could be 5x. Okay, add 1 to the power, divide by the new power, it's just ones. But I need to account for that constant, so I actually say 5x plus c. If my derivative is 2x, as I said before, it's going to be x squared. Add 1 to the power, divide by the new power, but I need to account for that constant. I don't know what that is. It could be there. It could be 0, or it could be 1000. 3x squared, if I add 1 to the power and then divide, I just get x cubed. I need to account for the constant. So this doesn't change, so it doesn't matter what we have, it's going to be the same thing. We get this plus c at the end every time. And it's just a constant term. It could be any number. We don't know what it is. So first example, finding a antiderivative of 6x to the 8. So if our derivative is equal to 6x to the 8, when we find our original equation of y, it's going to be the antiderivative of it. So basically, just add 1 to the power and then divide by that new power. We have a 2 and a 3, so 2x to the 9 over 3. Finding an antiderivative of 3x squared, take 5x plus 2. Because we've got a long equation, just like finding the derivative, we can do it individually in parts. So the first one, 3x squared, finding the antiderivative of it. I'll use brackets. So add 1 to the power, and this time I'm going to say multiply by the reciprocal. It's the same thing as dividing by 3. So I got my x, I'm going to add 1 to the power, and it's going to be a half. And here, initially I have a x0 technically. If I add 1 to the power, it's going to be x to the 1. 1 divided by 1 doesn't do much. Oops. Okay, so when you have a constant term like 2 or 3, etc., it's just going to be 2x or 3x. Now simplifying all that, we have the thirds cancel out. So we have x cubed, take 5 on 2, x squared plus 2x. And the last thing, just remember we need that plus c at the end, because we don't know what that constant term is. Whether it is there or not doesn't matter, so we just say plus c unless we can actually find it, which we'll have a look at in another example shortly. And the last one, we've got our f dash of x, or the derivative, is actually x. X take 1, x plus 1. So we're finding the original function by finding the antiderivative of it. And to do that, I probably need to expand those. If I expand it, I'm going to get x cubed take x. So now finding the antiderivative of it, it'll be x to the 4. So add 1 to the power gives me 4, divide by 4, take x. Now it's going to be squared, and I've got a half there. Final step is to add that constant. So writing antiderivative every time takes ages, and just like finding derivatives, we can use what's called or a special notation. So just like our derivatives was dy dx or f dash x, etc. Finding antiderivatives, we use a symbol that looks like this. It's like a long S. So finding the antiderivative of 2x would be x squared plus c. So that's an antiderivative. When we draw antiderivatives, we need to do dx at the end. Some people like to use brackets around the actual function and then put dx at the end. You don't need to unless you want to. Different people like to. Um, so just like finding the derivative, we have that dx at the end. Very important you put that in as just notation. So an antiderivative of 2x dx is actually x squared plus c. We've also got some properties of antiderivatives. So the antiderivative of one function plus or minus another function is going to be the same as the antiderivative of the first function plus or minus the antiderivative of the second function. And we had a look at that before where we had one function, another one, another one. We split it up into smaller bits so we can do that. That's essentially what that's saying. The other property that's important too is if we have a constant times a function and we're finding the antiderivative of it, well, it actually makes a lot easier if we bring it out the front and it actually works out like this. So that constant term, if it was a 2, we can bring that 2 out the front and just anti-derive the function that we're interested in. So there are two properties that are helpful in working some of the examples. I'm going to have a look at worked example 2. So it says find the use the unitary properties to calculate the antiderivative of 2x cubed plus 4x take 3. And to do that, I can find the antiderivative of 2x cubed first plus the antiderivative of 4x plus the antiderivative of minus 3. Then using the second property, I could actually just say bring the 2 out the front, bring the 4 out the front, and bring the minus 3 out the front. And to do that, quite simply, 2 times x to the 4 now, and that's going to be divided by 4. I've got plus 4, now add 1 to the power, divide by 2, take 3. Now that 1 just becomes x, divide by 1 doesn't do much. And then just tidy up. So I get x to the 4 and a half of that, 2x squared, take 3x, and we need to add that c. So that's the first example. The second one says calculate the antiderivative of 7x to the 5, 8x, 7 over 5x dx. First thing, like finding derivatives, sometimes it's easier to split up the fraction and make the equation simple before we find the antiderivative of it. So then I get the x's simplify, and I can bring out the 7/5 x to the 4, and using linear properties, I've kind of jumped a few steps in one there. So I brought the powers out the front, and I'm using that first property, splitting up the integral into 2 parts. And then it's just finding the antiderivative of it. So add 1 to the power gives me x to the 5, and this is where it's probably better to multiply by the reciprocal because I've got a fraction at the front. Adding 1 times 1, 7. 5 times 5, so I'll have 7 over 25x5, take, and 7 and 5 gives me 35 and 8. And then don't forget your plus c. And the last bit says find the antiderivative of x take 1 on x squared dx. To start off with, probably easier to expand those brackets. So if I did that, I'd have x and then I'd expand the brackets and I would get x squared take 2 plus x to the minus 2. And now it becomes a little bit easier to find that antiderivative. I'm not going to write it out, but we'd find it individually. So antiderivative of x squared would be add 1, divide by 3, take 2x. Now a minus 2, if I add 1, I get minus 1. So, and then I would divide by minus 1. Again, plus c, then just simplify it up a little bit. And that minus 1 just means it's on the bottom. And a minus just means I take away that. So that's the answer. So that's chapter 14 or part 14.2 of antiderivatives. Have a go at the questions. Thanks for watching.